Yeah. So as you can see on screen, I posted the problem set on the Discord channel, and hopefully this doesn't take too long for you guys to read. So I'll remove this sentence for now. Yeah. So we're gathered here today to do some strange non-standard functional equations. You guys already have had a class on standard functional equations, so this feels like a natural sequel. So yeah, let's start it right away. So the thing with functional equations is this, create a study at all, right? So several general things that the several themes that will keep popping up is, of course, substitute nice values. And the second thing that theme that I'll explain in a bit basically says come up with rich configurations. What does rich mean? What does configuration mean? We'll get to those in a bit. You know what come up with means. So I won't get to that. Yeah. So let's start with this is the first section. I have collected this huge list of 3 polynomial functional equations. So the thing with polynomial functional equations is there's not a lot of them. So it's sort of hard to pin down a general theme to for all of these, and even harder to come up with an actual strategy that works for all of them. So it's basically handled on an ad hoc case by case basis. But one general thing you can notice is induction. You'll see that. So yeah, let's start with. So I'd like some input from you guys as well. So I'll try to let you guys do some solving as we continue. Okay. So, yeah. Let's start with the first one. So Px is the set of, what's Px? It's a set of single variable polynomials in X with coefficients that are integers. We have to find all functions Px to X. So it takes a polynomial and spits out an integer. Such that the first condition is second condition is if this is non-zero, one tiny little thing to note here is on this side, this 1 is the constant polynomial given by 1, and on this side 1 is just the integer 1. So those sort of have different data types. Although for our purposes that won't really matter, but something to keep in mind. So yeah. Anyway, so one thing I should have started by saying is I sort of got lazy and I'm gonna recycle last year's lecture from last year's IMOTC that happened. So hopefully there's not a huge overlap between participants of that and participants of this. If not, I do have some new additions to the problem set, like to updating my problem set. So we'll get to those things. So even if you have attended that lecture before by some chance, it won't be complete waste of time, hopefully. So yeah.
Are P and Q any polynomials or some polynomials?
Sorry, say that again.
Are P and Q some polynomials or any polynomial?
Right, they are any polynomials.
Okay.
Yeah, so the first, usually a good first step to start with is, although there are exceptions, the good first step to start with is try to guess what solutions there are. Try to come up with examples of functions that satisfy these requirements. So any ideas on that front?
Theta of P is equal to P1s.
Say that again. Theta of P is equal to
P1s.
P. So this P is a polynomial, right? So you're supposed to spit out an integer.
Like this p is supposed to be integer. I've just misplaced the variable name.
Still don't quite understand. So suppose your polynomial is x² plus x plus 1. What does that map to?
I'm saying like theta of x is equal to x for all x.
Theta of x is equal to?
X works.
Sorry, say that again. Theta of x is equal to what?
Theta of x is equal to x.
2x.
No 1x.
Theta
Still
outputs
not
an integer value.
Theta
Not
is zx to
yes,
z,
still
right?
not an integer. So basically this will taken in polynomial and the output will be some and 26 or something. Probably not 26.
Is it theta of p equal to p evaluated at some point?
Yeah, that's a good example.
Maybe some of all coefficients.
Sum of all the coefficients, which is really a special case of the other example we just saw. So I'll just write that down. So we fix some integer n, and this is a function from zx to z. Take a moment to really capture what this means to have a function from zx to z if you're still not convinced. So basically what this function does is it takes in as input this p and evaluates that polynomial at n and spits out this integer. So if you evaluate an integer value polynomial, that integer is an integer. So this is a valid example. You can easily check that. So for example, I mean, I'm not going to do the checking. This is fairly obvious. And as someone else mentioned, some of coefficients is also a valid function, but that is actually the special case p evaluated at 1. So this is really just a subcase of this. So yeah, that's a good guess. Now we have to prove it. That's usually the hard part. So let you guys think about this for a second. So yeah, as always, it's always a good idea to start with small things, like plugging in easy things and see what comes up.
we can just take p as constant.
Sure, let's do that. But p as a constant, so px is a constant, so c. So this basically means theta of this constant polynomial. If this is something, then theta of so basically if you have this value at for some constant polynomial c, you have the value for every constant polynomial c, right? Because you can always get that by adding one, subtracting one. Did that make sense? So suppose, for example, we're looking at this constant polynomial 2, and we know that theta of 2 is say 5 or something. Then we know that theta of 3 is 6 and so on. Theta of 4 is 7, like this condition repeatedly. And you can also go back because then we can say that theta of 2, which is theta of 1 plus 1, is equal to theta of 1 plus 1. And we know this, so we can figure out this will be 4 and so on. So once you fix theta's value at one constant polynomial, that basically extends to all constant polynomials. I should have let you guys figure that out by yourself. I don't know why I'm blabbering, but yeah, that's it. Good observation.
If we take both p and q to be constant, we can
Yeah,
just
sure. That's also a good idea. That basically says whenever p divides some other integer r, I should take p. Let's take some other. Let's say a and b. If whenever a divides some other integer b, that means theta of a divides theta of b. Yeah, that's pretty good. It still doesn't really give us any values per se, but that's okay. We can keep looking.
we do have that theta of constant is just like some fixed constant plus constant. Because
Right, that's Good point. So we have that theta of C is C plus. Okay, how do I phrase a constant with respect to other constants? C naught. Yeah, oh, right. I can just do. Yeah, that's a good
We
observation.
have
So
theta of
this
C equals
basically,
C.
sorry.
We can conclude that theta of C is C from this.
How?
As it is linear and we have for every two
Yeah. So this basically gives you theta at any constant polynomial spits out that integer. That doesn't let you say figure out what theta of x square is, because you can't just keep adding 1 to c to get x square, right? Someone said note that theta of 1 cannot be 0. I guess that's a good observation. Why is that? Okay, what do we exactly expect this to be? Let's start with that. So assuming this is the entire solution set, um, what do we expect theta of 0 to be?
P divides 0, so we can say theta P divides theta 0 for every P. Then that should force theta 0 equal to 0. I think, maybe not. Because P plus, we can take P plus C and we can make the divisor as large as we want.
Yes.
But
Brilliant.
theta
Yeah.
of P can't be constant, right? If it isn't constant, then theta of P plus 1 should also be constant.
Yes,
Yes,
But
but
it
you
isn't.
have infinitely many such constants, right?
Yes.
So that size gets very big if you multiply all of them.
Yeah, to summarize that argument, every polynomial p divides the zero polynomial, which means theta of p divides theta of 0 for every polynomial p. So even if theta of p is some integer, say a, you can always replace this p by p plus some other big integer number, say n, and then theta of p plus n would be a plus n, and that would mean a plus n also divides theta plus theta of 0, and this n can be chosen to be as big as possible. So
There
what
are
is this?
infinitely many such things.
Yes, yeah. So what this is essentially saying is, no matter how big an integer you choose, it always divides theta of 0, and since this is some integer, there's only one integer that's fits that bill.
I guess theta of 0 is equal to 0 then.
Excellent. So we have figured out theta of c is equal to c for all constant polynomials. That's progress.
In the polynomial case, we need to work with the second condition, theta of P divides theta of P times Q. So since we know that it is a non-constant polynomial, so like consider some value of P such that theta of P is not equal to 0.
Consider some value of consider some polynomial p such that theta of p is non-zero. Okay.
Yes. So so theta of P divides theta of P times Q.
That is correct. Yes. Oops.
Maybe it just tries to like force the constant term of the polynomial theta to be 0.
Constant term of the polynomial theta. Theta is not a polynomial. What is
Oh, yes.
theta is a function from a set of polynomials to integer. Complicated to wrap your head around, but yeah, theta is not a polynomial. Yeah, this is a very good point since someone brought it up. Public service announcement. Stop assuming things are polynomial in functional equations. Last year, not last year, 2021 NMO grading. That was a nightmare because so many people assume the f is a polynomial. What does it even mean to have a polynomial on the set of polynomials? Think about what you're writing. I mean, you guys passed in, so probably you guys won't make that sort of mistake, but in general, spread this around as much as you can. Don't just assume things are polynomials. It's something physics people do. We don't do that. Yeah, back to our problem.
We can find theta on linear polynomial.
We can find theta on linear polynomials. Go on. That seems promising.
As in, we can show that for linear polynomials, it's of the form P of some value.
Go on.
Like suppose theta of x is something.
No. Hey.
Yeah. So we have theta of x plus c, whatever.
Yes, theta of x plus c is a plus c.
So if you want to determine theta of say cx, then we know that
cx, yeah, sure. Cx. Then
we know theta of x divides this.
yes, a divides this.
So we also know that if you consider cx plus a, cx plus c,
Cx plus c.
a plus 1 divides this.
Sorry, a plus 1 divides this, yes.
And it's also equal to theta of cx plus c.
It's also equal to a plus c. Theta of cx plus c. That sounds about right, yes.
Oh, never mind. This is not very useful.
But this is a good idea that taking some value of theta x, because this, remember, we want our answer to be that theta of p is p of some mystery constant. This constant is in fact exactly a. Because if this has to be the final form of theta, then theta of x has to be x evaluated at the mystery constant, which is by our definition a.
All right, we can just subtract c times the left-hand side from this.
We can subtract c times the left-hand side from what? So that I can c times? Okay.
C times a plus 1 from this.
So yeah, let me do that. So this divides CA minus C. Yeah, so this divides this minus CA. Yeah, that's okay. Yeah.
And repeat same thing with a plus 2, a plus 3, and so on.
Oh, nice. Yeah, that does work. That does work. Yeah. So basically, a plus any large number divides. This quantity. So this has to be 0. Yeah, and so that's progress. We now know that all we now know this for all linear equations. Is everyone following this argument so far? So what we have done is we are
shouldn't it be a plus n divides theta cx minus n times ca?
should it? Let me check the computation then. I sort of believe the argument on space.
No, the cn just cancels, so it's just c.
Yeah. Let me just check.
Oh, okay, yeah, okay. Then c.
So this divides cx plus nc. Which is theta of cx plus nc. So yeah, we subtract minus nc minus n. Wait, what just happened?
We subtract c times that, not n times c.
Right. Yes, thank you. Yes, this. So a plus n minus theta cx minus c. Yeah, this works out. This works fine. So yeah, now we can probably generalize this to the general polynomial. That should be what's right. Maybe not. Yeah, I don't plan to do any of the work in this class.
I think
Yeah,
I
we can
have
do the same thing with
something.
Yeah, go on. Someone was speaking. Yeah, go on.
Okay. Yeah, so I'm not sure if it's exactly what was done before linear, but like so you can say like
Yeah. Go on.
for any constant, okay, so if there's some polynomial p and we're trying to evaluate theta of p,
Mhm.
then for any constant c, right, we have x minus c divides the p minus p of c,
P of C, okay.
or p minus
We
p
got
of
it.
c, right?
Yes. Yes, yeah. This is probably more
Yeah.
naturally operating there, but yeah, excellent. So then
So
basically have,
yeah, theta of both sides.
yes. But we know this
And
is just
yeah, you can take the c out of the other side too.
yes.
Wait, is it minus theta of p of c? You can just write minus
Right.
p of c.
It's just P of C. But yeah,
And
it's the same thing, but yeah. And
the
this
others,
we know.
yeah.
This is A minus C divides theta minus P of C.
But then a minus c divides p of a minus p of c. So you get like
Basically,
a minus.
you just go on and just this back and forth is not productive. This is finish this. Yeah, we are basically done anyway.
Can you scroll up a bit?
Go on.
Can you scroll up a bit? Yes, thank you.
Yeah, I'll just continue from here. So from these two, we have a minus a divides theta of px minus p of a, and we're basically done because this side does not depend on c, and on this side we can take c whatever we want. So this has to hold for all integers on this side, which is only possible if this side is 0. So yeah, that's pretty much it. Yes. When you're writing this, there are certain cares to be taken because of remember this condition had this caveat that theta p cannot be 0. So there, for example, this cannot be this doesn't hold if c is equal to a or some nonsense like that. But this is infinitely many integers, so that's not to worry about. But yeah, when writing that, it's probably a good idea to take note of these final points. Yeah, everyone okay on board with the argument? I'll give a minute to let that sink in.
Yes.
Okay.
But now we can choose C to be anything.
Yes, exactly. Now we can choose C to be anything. So this integer can be whatever we want. And that effectively forces.
So we get that theta P of X is equal to P of A.
P of A, which is what we wanted, right? That basically means you give any polynomial and it spits out this integer P of A, where A is some fixed integer. That was the original goal.
Can we just try to generalize it now?
Generalize what?
Like we proved it for linear function, right?
Oh no, this P was anything.
Okay.
This P was general. So
Yes.
yeah, so this works in general, and we are done. Just convince yourself you're done. Though. It's not done unless you're actually convinced you're done. Yeah, I'm assuming everything is done. If there's a question, let me know. So yeah, so this is usually how the solutions involving polynomials and functions on polynomials look like. And yeah, there are two more in the problem set which I won't go through. Obviously, so move on to symmetry. So this is slowly growing in popularity these days, and one general theme I have that I have noticed before. One very useful trick to solve these is come up with rich configurations. Now, what do I mean by that? Take a look at the problem set. So the first problem basically says for each point A in the plane is assigned a real number. So it's a function from the plane to the set of real numbers, and it's known that this equation holds whenever n is a centroid of ABC. Okay. Second problem does similar things involving it's again a function from the plane to the set of real numbers, and it deals with the configuration. There's the triangle with its in-center, a set of centroid. Problem 6 is actually a special case of problem 7. Problem 7 basically says that whenever you again have a function from the plane to the set of real numbers, and given any regular n gone, some equation holds. So this, yeah, this, let's, I'll just
Are you doing
take it
the
out.
first problem?
No, we are not, I'm not doing anything particularly, again, pointing out a general theme in these things.
Okay.
So now problem 10, for example, see what that says. So P is a set of all points in a fixed plane and O be a fixed point on the set P. Find all functions f from P minus O to P minus O such that whenever this condition holds, AB equals AO. So we are looking at this plane minus the specific point O. And whenever we have 2 points, A and B, satisfying the condition that AB is equal to AO, something happens. So the point is, all of these functional equations are stated in this fashion. We have some function on the plane that carries something to something, and then we are given some configuration involving those somethings, and we are told that some condition holds in that configuration. So one useful trick that works in a lot of cases is come up with a configuration, come up with some figure in which that particular configuration occurs a lot of times and they interact with each other. So for example, in the problem 6, where it's a real valued function and it deals with squares on the plane, vertices of the square on the plane, it would be useful to come up with some sort of configuration that has a ton of squares. And ideally a ton of squares involving a small number of points, because then the squares only have to interact with each other. So yeah, this is sort of a good daily example. Let's do that, problem 6. So we have a function from the plane. So we are associating every point on the plane to some real number, such that whenever we have a square ABCD on the plane, the sum of values at its vertices is 0. We have to show, does it follow that if these 0 follow points in P? So the idea is, as I said, so I mean, if you have read the statement of this, you'll see that this is one of those examples I was talking about. So basically, you're given a configuration. In this case, it's a square, and you're given some information about this configuration. And like I said, usually a good idea is to come up with a figure that involves lots of examples of this configuration. So come up with some sort of figure that involves a lot of squares, that like sort of interact with each other, and that should be a good point to start. So yeah, now,
Cartesian plane you can use.
Cartesian plane is fairly big. It would be easier to do it with a smaller set of points.
9,
Even
Yeah,
like 9 points.
9 points, like how? Yeah, 9 points in 3 by 3 grid. Yeah, that is the promising because it's a return of circles. So give these things names. What's the good way to name 9 points? You don't want to go A1, A2, A3. You probably shouldn't be thinking too much about this. A, B, C, D, E, F, G, H, I. Now all it remains is, so this has an example of a lot of squares in this configuration, and all we need to do now is find those examples and play with them and see what pops out. So just do that. Where do we start? Of course, we have this equation. What else?
There's like the EFGH and
EFGH.
and then there's
correct.
like the AEIH and the 3 other
AEIH.
squares like that one.
Yes. So yeah, this is.
You can get a bunch of equalities there.
Get a bunch of what? Equalities. Yes. So yeah, AIH is a valid square to apply this condition on. So we'll say EBIF and so on. What do we do with them?
I got E equal to minus G.
You got E equal to minus G. That is promising. How did you get that?
So from AEIH we have F of. So instead of F of A, can I just select A? That is easy.
Yeah, sure, yeah.
So A plus E plus I plus H equal to 0. And from HIGD, we get H plus I plus D plus G equal to 0. So,
HIGD, yes.
So you get A plus E equal to D plus D.
Yes.
Similarly, you can get B plus C equal to C plus G.
B plus E is equal to
C plus G.
That is true.
So now, 1 second.
So
Yeah,
A minus B is equal to D minus C, but also A plus B plus C plus D is 0.
Right. A minus B is equal to G minus B. So, and also if yes, take everything to the side. Did I do that right? No, I did not do that.
A plus B plus C plus D.
Yeah. And we also have A plus B plus C plus D. Yeah, that is good progress. So that means B equals minus D. Okay, great. What now?
A equals minus C similarly. So like basically ABCD was a square, right?
Like this just means if you take 2 random points, then one
yes,
is
effectively.
Which
yeah,
means
so basically there was nothing special about these D and D points anyway. If you start with any 2 points, you can always draw this configuration around those points, right?
Yeah.
So that basically means if you take any 2 points, A and B on the so X and Y on the plane, and build this configuration around them, you can do the same logic to figure out that X plus Y is 0. So, and that feels like a fairly strong condition, right? And the next step is just not too hard. I'll just you can
just then substitute this to get that f of x equal to 0 for all x.
Does that help?
Yeah, we can just take 3 points.
Yes, taking 3 points is a good idea. Take some other point Z. So we have x plus y is equal to 0, y plus z is equal to 0, x plus z is equal to 0. And that's this whole linear equation. You solve that, you'll get that all of these are 0.
Yeah.
Does that make sense?
Yeah.
Yeah, brilliant. So yeah, this was not too hard of an example, but the point was to illustrate the idea that spamming in general is a good idea. You take some figure that has lots of examples of this specific configuration appearing on there, and do something with that. Like the more interactions happen between those sub configurations, the better.
But we also needed the fact that it was a square.
We
the next problem generalizes it to any regular algebra.
Yes, correct. The next problem is slightly hard. Okay, we can try that. Would we have time for that? Yeah, we have plenty of time. So it doesn't matter. I'm not going to finish all of this anyway. Who cares? Yeah, we could try something. Actually, you know what? I'm going to come back to that one. Not too much of a leap from 6 to 7, and then the cooler things to worry about. I think. Yeah, let's look at problem 10. Yeah, but after this, maybe I'll come back to that one. So yeah, let me stick in the statement again. So we have a set of all points on the plane P, and we are removing this one specific point O, and we are defining a function that takes points on this punctured plane through points on this punctured plane. And yeah, and what's the condition? Whenever you have 2 points A and B with this length condition holding, AB is equal to AO, that means in the image, f of p lies on the, so this is f of a, f of p lies on the semicircle. I'm not going to bother drawing the semicircle because clearly I'm bad at drawing them. So I'm just going to express this by saying this is the right angle. So yeah, first of all, let's start guessing. What are some example functions that actually do satisfy this condition? Actually, maybe draw the semicircle anyway. Doesn't this thing have a circle?
If we take OAB to be equilateral, then we get f of A is f of B.
You take OAB to be equilateral, then you get f of A is equal to f of B. That is correct. Because both of these angles have to be right angles, and that's not possible unless they coincide. Yeah.
So like the function just going to 1 point works.
The function going to just 1 point works, yes. So one example is constant. So it takes all the points to some fixed point. That's great. And I would let you guys think on this for a few more minutes and try to guess if there are other solutions. But this is going to be disappointing, so I'm just going to spoil that anyway. This is the only solution, the boring constant function. There's nothing else going on. And so basically, our claim is only solution is f of p going to some fixed point C. So now we need to prove that, and the way we usually prove this function is continuous is by picking two arbitrary points A and B and proving that A of f of B is equal to f of A. We already did that in the special case where OAB forms an equilateral triangle. So now we want to take two arbitrary points A and B and try to figure out if f of A is equal to f of B. And since none of these lengths has to be equal in the general case, it's probably a good idea to construct some more points so we get some points to apply this condition.
The circumcenter?
Oh, that's actually not a bad idea. Yeah, I have no idea what this accomplishes, but let's see. Yeah, so what this means is, sorry, O, FD. So basically, it's not that interesting to be honest. Basically, this means FA and FB both lie on this semicircle. It doesn't tell us much. Although it doesn't have to be the circumcenter, has it? We are not actually using the fact that these two lengths are equal. Oh, never mind, these two are equal. Yeah, this basically tells you that.
But then we can get a contradiction.
Go on.
Like then we can. Oh, no. Doesn't matter.
You may consider a point 2A, which is the reflection of O across A.
Okay. 2A.
So we have OF of 2A is less than OF of A.
O f of 2 is less. What is that? You mean lengthwise? I see. Yeah, that makes sense.
Yeah, then similarly, we can have OF of 2 to the KA less
Mhm.
than OF of 2 to the K minus 1A and so on.
Yes, that is true. Mm, Yeah, this basically gives information about points only on the single line, which is why it's probably not going to be that useful. But there wasn't one useful idea in this construction. So let me explain that. So basically note that in this configuration, A and B play two very distinct roles. A is sort of the elbow of this V shape, and B is sort of the other end of this shape, right? So in our mega configuration, in which we want multiple copies of that configuration to occur, what we ideally want is A and B, both of them occurring as both of those roles. So we want A to be the elbow of some of those V's and A to be the end of some of those V's. So in this example, for example, in this configuration, for example, that we have had, A does occur as the end of this V, and it's also the elbow of this V. So yeah, I made up some terms on the fly, so hopefully those are not too hard to understand. So point is, this sort of this sort of configuration is good in this sense because then you get to use A in multiple ways. So probably let's not take them all on the same line though.
Reflect O over AB.
Okay, reflect O over. Okay, I'm bad at trying this. Yeah. Reflect O over AB. Yeah. Then we have these two V's, and they basically mean, what does that mean? FO lies on this circumcircle as well as the other circumcircle. So, not fun to draw. And it also lies on the other circumcircle. Something like.
So if you pick a random point O dash, then the perpendicular bisector of O dash gets mapped to a line, like something on a line.
That is true.
Well, we can say that for any random line, right? We don't need necessarily
Yes,
line only.
exactly. Given any line, there's a perpendicular bisector of O and some other thing. Given any line, you can take this reflection, and then it's a perpendicular bisector of O and O dash. Then that means this line basically gets mapped to a subset of some other line. That's pretty good.
So if you just pick a point and multiple lines through it, then all those lines created must converge. And
That's
this
true.
must be
So basically, concurrent lines map to concurrent lines. This is actually pretty good. This basically means our map preserves collinearity and concurrency, so it's a projective mapping. Well, sort of, because it's not really on the plane, a punctured plane. But I think projective maps on the plane are easy to characterize, and that might be going a bit too hard for this problem. Yeah, interesting approach. So yeah, projective maps on the plane are characterizable, but projective maps on the punctured plane, I'm not sure.
Wait, so we can say in my previous example, I said that O f of 2a is less than equal to O f of a, right? And a and 2a lie on a line with passing through O. So their mappings must also lie on a line.
Oh, right. There's a slight problem there. This argument doesn't really apply for lines passing through O. Right.
Oh,
Does it?
No, that would require you to take
Yeah.
O dash equal to.
Yes,
oh,
yes, yes.
right, right.
Yeah.
Wait, so this means f of O dash lies on this line.
F of O dash lies on which line?
The line, the image of this line.
Oh, wait, is it? Oh, right, yeah, of course. Oh, that is interesting, because then you can take a line parallel through O dash, for example, and that would have to map to some line. Okay, no, never mind. That doesn't really do anything.
That means the images of two parallel lines also intersect in the plane.
That is okay. Hold on. So what exactly is the images of two parallel lines also intersect? Yeah, that is correct. Interesting. I mean, we know it's eventually going to be a constant function anyway, so this shouldn't be surprising, but it's still a strange condition to work with.
If we consider a line O dash passing through O dash and intersecting this first line at like some point K, then the image of this line should pass through F of O dash and F of K, right?
Right. So it has to be the same line.
Yeah.
Oh, okay. So pretty much all other lines pass through. So pretty much all other lines map to the same line.
Except the parallel line.
Although all those lines except this line. So basically, the entire plane maps to this line except this parallel line. Oh, this is actually pretty cute.
Oh,
Hold
but
on.
this parallel line, notice that this parallel line it intersects at one point only.
Yeah. So, this is actually pretty cute. Let's see. So, so the entire plane minus this one line all maps to points on this specific line.
You can like repeat same argument with some
yeah, that's exactly what I was gonna say. This entire plane minus this specific line maps to points on. Okay, it could be the same line though. That's the problem. Could it be the same line? It can't be the same line because
If we have the same line, this implies same point also, because you
yes,
need
yes,
some
yes,
line
right, right, right.
and there's only
The
one
circle,
point that can do it.
right. The circle thing doesn't work out then. So basically, the entire plane minus this specific intersection point maps to the same point. Yeah, I'd say this is pretty much standard. Constant function is probably provable by some minor argument. We can finish it if we have time, but yeah. This is fun. So what's the argument exactly? Yes. So this entire plane minus this particular line maps to this specific line, and this holds for any line. So
It's like if we pick a random point that's an elbow, it has to map to the foot of perpendicular.
right, yes, that pretty much covers every line in this, I believe. So yeah, so these two either suppose they are line, yeah, so they have to map to this foot of perpendicular. Right, right, that makes sense. And this elbow could be anywhere, I am guessing. Yeah, that
Anywhere
makes
except
sense.
that one parallel line.
Yeah, but like this, yeah, except these, except this one parallel line, the elbow could be anywhere. Oh, brilliant. And okay, this is hilarious. And you can so basically what we're saying is in this configuration, all the points. So you can always make a point into an elbow, right? So that means all the points actually map to the same point, which is this perpendicular. So every point on this plane, apart from those on this parallel line, map to this point. And we can do the same argument with some other thing. So clearly, these two, since these two have to be, all points on this plane minus this L2 also map to the same point, and they have to be the same point because these two sets of points in common. So everything maps to the same point except for this one point. That can be fixed by just taking a third point. Yeah, you're done. Right?
Yeah.
Nice. So we should probably clarify the argument for people who are. Yeah, I am doing too much of the solving this lecture than I expected to. I mean, it was basically you, but yeah. Yeah, this is great. So just to summarize the argument, you have some point, you take a random O dash, and you consider the perpendicular bisector of that. Then what happens is yeah. Yes, so you take any point A and B in there, then do the usual mumbo jumbo to figure out that this basically all these points lie on the same line. What was it that we did after that? And then we took a point through O dash and use the same things to figure out that all of these also pass through a. Yes, I remember now. So just to recap, so we have this O dash, and you use the condition to figure out that f of A, f of B, and f of O dash are collinear. So all of this entire line maps to this one singular line that also contains f of O dash. And if you take any other line passing through O dash that intersects this line at some point, and it also oh wait, there's one little caveat. This line passing through this intersecting line cannot pass through O. So we are actually
All
missing
but
out
two
on.
lines.
Huh? Yes,
So
all
all
but
but
2 lines.
that's just so
This is getting annoying. I'm just gonna handle the rest of it. Yeah, so everything except these 2 lines. So if you take any point on everything except these 2 lines, yeah, that has to map to the same line. It has because you can always take this line passing through O dash, and that has to map to some line that contains one little problem though. This line can just be, oh wait. Yeah, the problem is, so this k, right? What if f of k is equal to f of O dash? Then you can't say anything. You can't say that this line is the same as this line. This line maps to this line. Okay, this is disappointing.
Suppose there exists a k on the line such that f of k is not f of O dash.
Well, okay. That basically takes care of all points on that particular line.
Yeah. Okay, but by symmetry, the reflection of O across this new line you added, that also f of that thing should also become equal to this.
F of that thing.
Should
Wait,
also
what?
equal f of k. Because from that, oh no.
Right. Yes, that makes sense.
And can we consider some other point O double dash such that the line BO double dash, the line BO double dash will also map to this line. So f of O double dash must lie on this line too.
Interesting.
And this line must also be perpendicular to f of O double dash. Wait, no, not necessarily.
Yeah, I'm sure there's probably some sort of argument along these lines. I don't want to spend too much time on this, but we can try. You guys can try. Too old for this. You guys can try going along this line for some later point. So yeah, I won't explain the solution that I had in mind because having a solution, knowing a solution sort of discourages you from looking for other solutions. So I want you guys to keep working on this idea because this looks very promising. So yeah, we'll take a rain check on that one for today. Put that on hold and I'll move on to other problems. Yeah. So yeah. Also a note to myself. Do you like this idea? This seems promising. So yeah, let's move on to the third section of the problem set. So this is the set of this is the part where I'm listing functional equations or problems related to functions where the central condition is not really an equation. It's still over real for integers or some of the nice normal familiar stuff, but the central condition is not exactly an equation. It's a statement. So yeah, let's try 16. Find all functions n to n. Is that whenever you have distinct x, y, z, says that this is a perfect square. Fx plus fy plus fc is also a perfect square. Yeah. So first of all, we can start by guessing the set of solutions. What do you think that would be?
C square x.
Yeah. This is a valid solution, and I mean, it sort of seems obvious that this has to be the only sort of solution, right? Nothing else nice seems to work. Yeah, so we can try proving it. So of course, always the idea with these sort of problems is you can sort of try to find triples that sum to perfect square, ideally a lot of them, and sort of try to see what information you can glean from that. So, yeah, I don't want to spend too much time on the. So what I'll do is I'll give you some basic outline of steps to follow. So first of all, try proving. Actually, that's not necessary. Let's see. So basically, what we want to do is try. So we want to prove that fx is linear. First of all, once we have that, the rest should be easy. So one good way of proving things are linear is basically proving that fx plus 1 minus f of x is constant, which would be equal to f of 2 minus f of 1. So let's try to come up with triples that use x plus 1, x2, and 1. Because that means we can use them.
How did you get f of x plus 1 minus f of x constant?
Yeah, so basically we're trying to prove that fx is linear, right? So if we do manage to prove that f of x minus x is constant, then we would be closer to our goal. So we are trying to prove that. We don't know that yet. Trying to prove. So to that end, we want to find triples x, y, z, where this x plus 1 appears and maybe x appears, maybe 2 appears, 1 appears. Maybe not one triple per se, maybe multiple triples. But yeah.
We can do it by, we may do it by induction.
Yeah, go on.
Suppose for we know that for 0 to n we know that f of x equals a square x, and then we prove for n plus 1.
Yes, go on. Yeah, I mean, induction is a good idea. Point is actually doing that, right? So yeah, so what we're suggesting is come up with triples that use these numbers. So one possible solution would be, so you use x plus 1 here, say 1 here. So the sum of this has to be a perfect square, right? Say a square. then you can use x here and 2 here, then these, and if you can make that equal to a square as well. No, use a different n square. These two can be the same number, which is useful. So if this is x square, this one, and their sum is n square, this has to be n square minus x minus 2. And similarly, this has to be n square minus x minus 2. So that gives us this is a perfect square. So yeah, running out of letters. M square, p square, and
If we show f of large is large, we are done.
that is correct. Let me just get there. Yes. So basically, what we have here. So once we have this, obviously the good way to. The obvious next step is to subtract these things to get rid of this, which would be which would give us. This is a difference of perfect squares. Now, difference of perfect squares get large as you get large, as someone mentioned. So basically, if this is a fixed number, this doesn't depend on n. But if you keep growing n, hopefully, we don't know that yet, but hopefully this part would keep getting larger, which would mean p and q will have to keep getting larger as well, which would mean that which would give a contradiction, because the difference between two perfect so p square minus q square. So unless this is 0, this is at least p plus q, because this is p plus q minus p minus q, and unless this is 0, this difference is at least 1, so this is at least p plus q. So if we can find n square such that this is very large, that would automatically mean p and q have to be very large as well. So this will have to be very large as well, which would be a contradiction. This is a fixed thing that doesn't depend on n. So the only thing to guarantee is f of n minus something can get very large. We can actually do something better. We can actually prove something stronger. We can in fact prove that f is injective. Does anyone see why f being injective would imply that f of this thing can get very large?
Yeah,
Wait, what
because
did
if
you
f
ask
of
again?
Yeah, so basically we're trying to make sure that by growing n, we can make this quantity, something is in constant 6 minus 2. This quantity we can make as large as possible, as large as we want. So my claim is f being injective already implies that. So does anyone see why it does? What if we can prove f is injective? Why does that automatically mean that this can get as large as we want?
because it can take finitely many small values.
Yes, effectively. And is everyone on board with that? This is like, so if you have to a lot of these Olympiad number theory problems that deal with analytics, like not analytics, I won't say analytical entity, but sort of this analytical ideas, which might seem familiar, but in general, this can be a tricky idea to wrap your head around. So is everyone fine with that?
Yes.
Okay, I'm assuming you speak for everyone. So if is injective, if is injective, we will be done. So let's try that. So the first step of proving injectivity is assuming there's a not equal to b, such that f of a equals f of b. So we need triples involving a and b. So we can sort of use the same trick as before. And
we can just say a plus c plus d is perfect square if and only if f of a plus f of c plus f of d, which is again if and only if b plus c plus d.
Perfect square if and only if a plus d is perfect square, which happens if and only if f of b plus this nonsense is perfect square, which happens if and only if b plus c plus d is perfect square. So in other words, the c plus d can be 1 integer. So a plus z is a perfect square if and only if b plus z is a perfect square. Now, does this look plausible? This doesn't look plausible, right? There's no way this is true. If you take, so basically that means is the difference between these two perfect squares is something constant, and we all know as the numbers get bigger, difference between perfect square get bigger and bigger. So that can't be possible. So let's try to formally prove that. So suppose we take z to be something k square minus a. So what that says is b plus k square minus a has to be perfect square, say L square. So b minus a has to be L square minus k square, which is again the same sort of argument holds. Does anyone see why this immediately gets to the contradiction? Just to recap, we have obtained that a plus z is a perfect square if and only if b plus z is a perfect square. We're trying to prove that a is equal to b. So assume it's not. Yeah, for large L and k, it goes to infinity. That's correct. So basically, if it's not zero, it's at least L plus k. And if you keep taking a huge k, this has to fail at some point. So the only option is L and k are actually equal, which would imply b and a are equal. So that implies injectivity, which in turn implies that this is unbounded, which in turn implies a condition. So yeah, that's no problem down.
Wait, actually, can you repeat the argument for injective implies none?
Yes, yes. Good point. So what we saw here is, so we took these two triples and figured out that this quantity is equal to p square minus q square. And if p and q are not equal, which means if this is not zero, then this is at least p plus q. So if we can ensure that by taking large n, this can be made as large as possible, as large as we want, sorry, as large as possible. If we can ensure that by taking large n, this can be made as large as we want, then p can get as large as we want, which means p plus q can get as large as we want. That immediately gives a contradiction to the conclusion that this is bigger than or equal to p plus q, right? So the only thing we need to make sure is we can make this quantity as large as we want by taking larger and larger values of n. And my claim is that actually follows from injectivity. So why is that? So suppose it does not. So if you keep putting n, this quantity is bounded by some n. But the point is, after some point, you will run out of values. So if you, since there are infinitely many possible n's you can take, and all of these values have to be bounded by n, at some point, two values have to clash, which would contradict injectivity.
Right.
Does that make sense?
Yes.
Oh, awesome. And so that's why we try to prove injectivity, and we did prove injectivity. So that basically gets done. Yeah. Now what I want to do is let's do 21. So this section is for functional equations that deal with other functions. So the conditions are usually something like for all functions this happens, or something like that. So we want to do 21 next because this illustrates important technique, at least one of the solutions. There's multiple solutions to this. So yeah, let's do P1. So the question says, find all f z to z says that for all surjective g, f plus g is also surjective. So as always, we start by guessing.
F is a constant.
F is a constant. That works. Does it seem like anything else would work?
No.
Yeah, nothing else would. So basically, we want to prove that f is a constant, which is saying that given any a and b, we want to prove that f of b is equal to f of a, which is saying that in case f of a happens to be not equal to f of b for some a and b, we want to derive a contradiction. So what would constitute as deriving contradiction? That would be coming up with some surjectives g, such that f plus g is not surjective. So this we have basically reduced this problem to some sort of construction. So suppose f of a is f and f of b is t, which these two are not equal. So we have to come up with some surjective function g, such that f plus g is not surjective. So yeah, so try that.
If g is equal to minus f of x.
G is equal to minus f of x. Why would g be surjective? We don't know if f is surjective.
Like we are considering it to be surjective.
Yeah, sure. That tells you the case that f, the special case that f is surjective, but in general we don't know if f is. We just have this one information that it's not constant.
Okay.
So I guess what that does prove is that surjective f cannot be. So f cannot be surjective. Is what we have proved so far. Which is something.
Yes, so we have some finite set of values that f takes. Like
We
some
have some
set of values. Not finite, like some set of values.
Yeah, we have some set of values that f takes. Is that what you're saying?
Yes.
Yeah, sure. That is true.
I consider that set to be S.
Okay. So the image of f is S.
Now, if we consider for the sake of contradiction that f plus g is surjective, then we can take like some element of S. It's just that f of f plus g of a is equal to that S, small s.
Okay.
Which is just f of a plus g of a is equal to s.
Yeah, sure.
We have that g is surjective.
We do have that g is surjective.
Yes.
So you are not taking a specific g, is it? You're just proving this in general.
Yes, I'm trying this. If we have some like more than more than or equal to two values of a such that f of a is equal to that s itself, then we would get a contradiction.
If we have,
like if we have for any a, f of a plus g of a is equal to s. And if we get that f of a is equal to s for at least two value of s.
F of a is equal to s for at least two values of s. Why would that be a contradiction?
Two value of a.
Okay, so say f of a1 and f of a2 are s.
Yes. No, like not that s, it can be s1 and s2. They can be
Okay.
And we are that f of a1 plus g of a1 is equal to s1.
Okay.
And f of a2 plus g of a2 is equal to s2. Which just tells that g at 2 points is equal to 0. Then it could be a contradiction.
That's not a contradiction though. G is surjective, doesn't need to be injective.
Yes.
Surjective means
yes,
so
yes, I got it.
Yeah.
Like consider G of A to be some K of A plus F of A.
G of A to be
Some K of A plus F of A.
K of A. Okay.
It would imply that K of A is also surjective since F is not surjective.
Wait, what now? Why?
Like because G is surjective. So we can make G to take any values.
Yes.
Like we want some M plus M is equal to K of A.
We can make G to be G to take any values and
we can take like some we need to prove that some M is equal to K of some J.
sure we want J such that this holds that.
Yes. So we have take some A such that G of A is equal to M plus FA.
We take some A such that G of A is equal to M plus FA. Why would that exist?
Because since it because since it is surjective and F of A is not surjective.
Why does that mean this A would exist? What you're claiming essentially is G minus F is surjective, which I don't think it's true in general.
But if F plus G is surjective, then we have like some G plus some values of a set is also surjective.
Wait, say that again. If we have F plus G surjective,
like since F takes
since F takes
like then F takes some value from a set S, then G of A plus some value in that S is surjective. We can choose such A.
What? I don't understand. Take some value S in the set A. So
we
G
can
of
find
A.
some, yes, we can find some A such that G of A.
We can find some A such that G of A. Yes, so these are good ideas. We don't have a lot of time, so let me just go through the solution. So the main idea is the fact that we have this set of integers in order that does not matter. So all we want is, so we have some list of numbers. We have some f right on z. So on z, so suppose we make a list. This is the elements of z, and f has, we have a list here, and we know that this is not constant. So all we have to do is come up with some other list of numbers so that this contains all the integers, but this one does not. Now the key point is this order you put these numbers in does not matter. You can switch around rows with no problem. In particular, you can basically enumerate these integers, this set C, in any order you like, and solve the problem from there. So take some enumeration of these integers. Say one very common enumeration would be 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on. So one thing we can try is, we already have f. Now, what about g? G we can define. So at each stage, so this is f of 0, f of 1, f of minus 1. We want G to this list to have all the numbers. So at each stage, we define g of 0, for example, to be the smallest integer not yet chosen and not equal to the, so basically we want f plus g to be not surjective. So it's enough to make sure this function f plus g misses one number. Let's fix one number, say 0. We want to make sure that 0 does not appear in this column. So let's pick g in this way. So g of 0 would be the smallest integer that we have not chosen yet, and which is not also equal to minus f of 0. And so if we call this S1, S2, S3, and so on, g of Si would be the smallest in absolute value, let's say, integer not chosen yet, and not equal to minus f of Si. So does this always work? Well, no, this doesn't always work. But when does it not work? So the condition that f plus g is not surjective, that follows from definition. So the only way this construction could fail is when g happens to be not surjective. So which means there's some number that does not occur in this column, say c. So when could this occur? So since you're choosing the smallest integer not yet chosen, that has to get picked at some point, unless it happens to be equal to minus f of Si a lot of times. So unless C occurs as so unless it so happens that after some point all these minus f Si's are equal to C, then of course C will never get chosen, and that's the only possible case where C never gets chosen. Yeah. So the only scenario where this does not work is when f of Si is equal to minus C for all I bigger than some large n. So this column basically goes T1, T2, Tk, and then it's all C's. So we need to deal with this case separately. So what we do then? So again, we just need to make sure G is surjective, and we can't let f plus g attain the value 0, so we can't put minus c in any of these. So minus c has to come here, and these can be any number, so that this does not equal 0. This can be anything not equal to minus t2, not equal to minus t3, and there's
Just
some
note
final.
that we can manage it easily. Like if some value can't fit in the upper set T1 to Tk, assuming that there T1 Tk are not equal to C, then we can manage it in the later
Yeah.
C easily.
Correct, exactly.
It just
So we can
it just becomes subjective when all of them are equal.
Yes. So basically, we can put whatever we want in here as long as the sum does not equal 0, and then we have some integers left that we have to put in this column. We can just enumerate them and put them one after another. That's pretty much it, right? Yeah. So that's the idea. Let me know if there are any questions on this. Because
Like
this is sort of
what
important.
problems use the same trick as this in the P set?
So I'm actually going to mention that. So this main idea here is enumerate the integers and sort of maintain a table and fill them up one after another. The similar idea would work in problem 24. So I like you guys to try that on your own in your own time at some point.
I wanted to ask a thing about the problem. So,
what did you want to ask?
like in problem 2, it is written f maps the 0 polynomial to itself. What does it means?
Problem 2.
Yes, it.
Yeah. So yeah. So we have a function that takes in real polynomials and spits out real polynomials, right?
Yes.
This basically means the image of the constant polynomial 0 is the constant polynomial 0. Okay. Yeah. So yeah, if there's any more questions, feel free to ask. And since we have a little bit of time, I'll take that few minutes to explain the mm, intended solution for problem 10, the, the V configuration elbow thing that we were trying. So yeah, so the idea is you have O here, A here, and B here. So idea is to draw as many copies of this elbow configuration as possible. So what sort of points make elbows with O and A? Well, it's all the points in this perpendicular bisector, and those cases O is the what do you call it? O is the edge of the V. And so let's make a configuration. Let's pick a point for which A with that point would form a V, and B with that point would also form a V. But B would be the elbow and A would be the edge. So how do we do that? So that point has to lie on the perpendicular bisector of OA, and we want B to be the elbow. So that point has to lie on this circle centered at B with radius BO. So it's the intersection of these two things. You can take either intersection, does not matter. Let's call this D or something. Similarly, so what's the special about this point? So this is a V, and this is a V. Similarly, take a point C, says that it forms a V with B as at the edge, which would lie on this perpendicular bisector of this line, and also forms a V with A as the elbow, so it would lie on this circle. So let's just see. So the special thing about this is this forms an elbow, and this forms an elbow. Yeah, that's all the point we need really. So let's try to see what we can do with this. So this elbow, this means O here, F of D here, F of A lies on this, what do you call it? The semicircle, the circle with diameter OFD. So what other V's do we have here? We have this one. This means C lies on this circle with diameter OFA. So what we have involving C, we have yeah, we have this this V, where C is the elbow, and this basically gives us that B lies on the circle with diameter OFC. And what's the final V we have to use? It's this one, where V acts as the elbow. So this basically tells us that F of D lies on the circle with diameter F of B. Now, is this impossible, or is this get us done?
It is impossible as the distance is going to shorter and shorter.
Yes, exactly. So F of this is smaller than this is smaller than this is smaller than this, and this is smaller than this, well, smaller than equal to. So the only way this could happen if all of these are at the same point, which basically means F of A is equal to F of B. Except there's a small caveat here. To construct these points C and D, we took some intersections, right? And in general, those intersections need not exist. We are intersecting a line with a circle. Who knows if that line even intersects that circle? So if you carefully plan out the details, you will see that those intersections exist only when this length AB is smaller than this length ON is smaller than this length AB. So you just need AB to be the shortest side in this triangle. So what we have proven here is whenever this happens, AB being the shortest side of this triangle, this FA is equal to FB. And that pretty much gets us done, because if you then take two random points A and B, you can take a lot of time points in between so that this condition holds for any of the consecutive points. And then f of a is equal to f of a1, which is equal to f of a2, and so on. And like that, you can get to f of b, and then f of a is equal to f of b, and that gets you done. Yeah, sounds good to everyone. Any questions? Yeah, I'm assuming that means no question. So you guys should try to see if that line idea works. I think it should work, but give it a shot. And try
Also, I
to.
think I have a completely different solution to that.
Oh, go on.
Like
Don't
it's
have a lot
based on
of
what
time.
Akshat was saying
Uh-huh.
about like the distance of like, so define d of a as the distance OFA.
Mm-hmm.
So the problem says that if OA equal to OB, then
Mhm.
d of A is at least d of B.
No, the problem is if OA equal to AB,
Yeah, sorry, AO is AB. Yeah.
then
D of A is at least d of B.
D of A is at least D of B, correct?
So essentially, like you draw the perpendicular bisector of OA
Mm-hmm.
and then intersect it with the circle with center B and radius BO.
Right. Let's see.
So then we get that f of A is at least f of B, which is at least f of C, which is at least
Right.
f of
Right.
A.
Right. Wait, no, that isn't. Hold on. This gives you this configuration which says D of C is at least D of A. Yeah, that gives you D of C is at least D of B. D of B is at least D of A. Yes, correct. And
But because of the I'm picking A and B to satisfy like OA.
sure, the intersection properties and whatnot.
Yes, you just get that D.
Right,
D
and
of
you can do that in the reverse, and that basically gives you D of A is equal to D of B. That's
Yeah.
the same thing, right? That's basically the thing we're doing here. Yeah, but anyway. Yeah. So nice. So we have several solutions, but I would like someone to complete the idea we're talking about before that. That's it. If you guys have any questions, let me know now or in the Discord. And with that note, I'll end you. You guys have something after this, I believe. Okay. See you. Bye bye.
Thank you for the class.